So we ended the last lecture by looking at a wire and recognizing that when an electron wanted to move through that wire, it's not going to follow a perfect straight across path. That the current we're actually measuring is the net flow of electrons. Okay, and so as a electron sort of moves through, or electrons try to move through this, they're impeded, and this impedance is called resistance. Okay, it's impedance of the flow of charge through a material. Okay, and it's dependent on several variables. One variable that it's dependent on is the material. So what kind of material is it? How good of a conductor is that material? Another is the size and length. Okay, and then the third thing is the temperature. Okay, I'm sure you've heard, like, if you have a server for a computer, one of the things that affects the ability for the server to function properly is the temperature of the server. So we try to keep electronics from getting too hot, otherwise they stop working. The increase in temperature actually prevents the movement of electrons, and so our electronics start to break down and not work properly. And that's why most electronics have some sort of fan system or vent system so they can stay cool. Okay. So the equation for resistance actually relates these two things. And the equation is that resistance is equivalent to resistivity times length over cross-sectional area. Okay, so this is resistivity, and this is a property of the material, so of the metal or whatever is conducting the electricity. Okay, so it's pretty much how easily naturally does that material allow electrons to flow. This is the length, and this is the cross-sectional area. Okay, now this is kind of backwards, because remember, the whole point of building electrical equipment or using electrical wires is to get charge from one place to another. Okay, but out of necessity, we have to build these sort of like long, thin wires, right? So we have all these long, thin wires. They're traveling across, miles of land to bring electricity to places. They're traveling through the walls in your house. So we have these long, skinny wires. But if we look at the equation, the longer the wire and the skinnier the wire, the more resistance, okay? So long and skinny has a very high resistance, but short and fat has a very low resistance, which is desirable, right? However, out of necessity, we have to have these sort of long, skinny wires, okay? Now, resistance, like we've said, relates to the flow of electrons. It's what sort of slows down the flow of charge, okay? So let's sort of relate this idea. Remember, if I hook a wire up to some voltage source, so I've got a positive and negative side, so I've got some source, maybe it's a battery or something, which is going to make a current, right, which would be in this direction. If we're talking about, remember, electrons would flow this way, so the current would be that way. And then the resistance is what prevents the flow. So there's this balance between voltage, which is the push, the resistance, which is the resistance of the movement, and therefore then the net move. And this is called Ohm's law. Okay, and the equation for Ohm's law is that V equals IR. Okay, so volts equals current times resistance. And this is what defines our unit of resistance. So if we solve for resistance, V over I equals R. And so we've got volts over amperes, so volts over amperes, and we call this an ohm. Okay? Now, if I wanted to determine the resistance of some material, I could do this experimentally in a lab, okay? Now this is a rise over run relationship. So let's say I wanted to determine the resistance of a light bulb. I could hook that light bulb up to a battery, right? Here's my light bulb. Okay, and somewhere I could measure the current. This is an ammeter. That's how it's drawn in a schematic. We'll learn more about schematics next time, okay? And an ammeter measures current, okay? So let's say I got a 12-volt battery and I plug it up. I could measure the current running through the wire, and then that would tell me something about the resistance of that light bulb, okay? So if I was going to do this experimentally in a lab, okay, what I would want to do is I'd want to plot volts and current, okay? And the slope of that would give me the resistance. So I start with 12 volts, then maybe I put in a 9-volt battery, and then maybe I hook it up to an outlet like 120 volt. So I can actually plot the change in the current, you know, as I change the push and pull. And so I would plot some data points, get my best fit line, and then the slope of this line is the resistance. Okay? Now, for things that are considered to be ohmic devices, these are things that are made with conductors, like really good conductors. The slope should be linear, okay? If you ever get a graph or see a graph like this, okay, this is considered to be non-ohmic. It doesn't follow that linear relationship. And this happens with materials that are considered semiconductors, which just means that they're materials that aren't full conductors. They don't allow electricity to flow very freely through them. They're substances like germanium, silicon. Those are metalloids on the periodic table. So just keep in mind that not all substances are perfect conductors and have this ohmic relationship. Sometimes they're said to be non-ohmic.